Hi everyone and welcome to this new video. We continue with the power factor correction examples. This is our example number 4. This is the question in place here. We have two loads connected in parallel and draw a total of 5 kilowatts of power at a power factor of 0.7 lagging from a power supply voltage source of 220 volts RMS operating at 50 Hz. And one of the loads observes 3 kilowatts at a power factor of 0.6 lagging. So if we make a sketch of this information, we will have the following, which is shown on the left. So we have a voltage source Vs with a value RMS value of 220 volts, 50 Hz operating frequency. We have one load, another load here, two loads in parallel. One of the loads has given information of 3 kilowatts of true power and a power factor of 0.6 lagging. For the other load, second load, we don't know much. So let's look at the questions. Calculate the power factor for the second load, so this one. And for the question B is calculate the required parallel element to correct the power factor, so such to increase the power factor to 0.95 lagging for both loads. So we need to increase the power factor, the complete power factor, from 0.7 lagging to 0.95 lagging for both of the loads. So let's start first with a situation of what will happen if you look at the total circuit. So the voltage supply Vs, the supply is power to both load 1 and load 2. So the P total, or S total, apparent power of course, the S total will be S1 plus S2. So that we can write the following. We can say S total, which is a total apparent power, will be equal to the summation of S1 and S2. Okay, then what is S1 and what is S2? We already know S1 is the load, the apparent power load 1, S2 is apparent power load 2. What is S total? If we write down this in a different form, S total is also equal to P total plus JQ total. Okay, we already know P total because of this 5,000, it's already given here. We don't know much about Q total, and we also don't know much about the S total. But if you make a drawing of the situation, some of the unknowns will be more clear. So let's make the real axis and the imaginary axis clear. So this is the real and this is the imaginary. So I'll make a drawing for the apparent power, the true power, and the reactive power for the total. So the supply. Okay, so we have the P total, which is actually this arrow and the real axis. So we have the apparent power as total. Of course, we have a phase, and I will denote it as T total. And there is, of course, I will denote this in green, the reactive power Q total. Okay, so we have the S total, Q total, P total, so we can write the following. S total vectorially is equal to P total plus JQ total. Okay, so what do we know? Now from the information shown above, we can see that the power factor is initially 0.7 lagging. That means the following: the power factor PF for the total situation initially is 0.7 lagging, and I can calculate from this the theta total using the formula R cosine of the P total, PF total. So I can have R cosine of PF total, which will give me the following: arc cosine of 0.7, which is approximately 46 degrees. It's a little bit less, 45.6, but let's round it off at 46 degrees. Now I can calculate both S total and Q total because I already know the phase, so it's actually all of the information can be calculated now using the phase and the P total. So let's first start with the S total. So what we have is the cosine of theta total will be equal to P total divided by S total. Now this will mean that the S total is equal to P total divided by the cosine of theta total. If you substitute the values given above, you have the 5000 divided by the cosine of 46 degrees, and it will give you approximately 7143 volt amperes. So that's actually for the apparent power for the total, for the voltage supply. So that will be the S total. What will be the Q total? Now if you use the sine, or you can also use that's also possible, you can also use a tangent, so you can use this arrow and this arrow, which is actually the same as the green arrow. So if I make this as a green arrow, so I can place the same green arrow here. So I can use tangent, so let's use tangent. So yes, let's say the tangent of theta total will be equal to the Q total divided by P total. In a similar way, Q total will be equal to P total times the tangent of theta total. Now if you substitute the values, you will have, I will move a little bit to the right side, we will have the following is 5000 times the tangent of 46 degrees, which will give us the value of 5103 volts ampere reactive. Now if you now have the Q total, of course on the S total, and we already knew the P total, we can actually fill in this formula. So what we have is the following. Then S total is 5000 plus J 5103 volt amperes. That's actually the situation for the total apparent power. So let's look at the load 1. What will give load 1? So this is load 1. What do we know from load 1? We know from load 1 is that the S1 is can be also divided in P1 J Q1. We know what P1 is, because P1 is 3 kilowatts or 3000 watts. We know what the power factor of the first load is, which is 0.6 lagging, and this will result in the theta 1 for the for this situation, which is again the same formula, arc cosine of the power factor, which will give us approximately 53 degrees. Okay, that's actually for this situation. If I now follow the same procedure and I calculate the Q1, so how do I calculate the Q1? So Q1 will be S1 times the sine of theta 1, and I don't know the S1, so what is S1? S1 will be P1 divided by the cosine of theta 1. So what do I have? I have the following, that's 3000 divided by the cosine of 53 degrees, and if I calculate this correctly, I will have 5000 volts amperes. Okay, that's for S1. Now I can calculate using this S1, I can calculate Q1. Then we have the following. The Q1 will be 5000 times the sine of 53 degrees, which will give us Q1 is equal to almost 4000. So it is 3998 volt amperes reactive, almost 4000. Okay, so we can now write the S1 also in factorial form using the Q1, which is calculated here in the given value of P1. So what we have is the following. Then the S1 will be 3000 plus J, almost 4000 actually, and this value, which will give us the S1. Okay, this is the situation for S1, for load 1. So load 2, let's move to load 2. So what we have is the following. We know that S total, we already written that before, is S1 plus S2, and I can now calculate the value of S2. And why is the value of S2 important? Because from the value of S2 I can calculate and determine the power factor for the second load, load 2. So if I write down S2 is equal to S total minus S1, and if I fill in the values I have determined, which is S total is given here, it's 5000 J 5103, so I will do that also. So it will be 5000 plus J 5103, I will make it in parentheses, and this S1 will be of course this here, so that will be 3000 plus J 3998, and the value for S2 can be calculated by subtracting the real parts and the imaginary parts. So what we have is the following. S2 is equal to 2000 plus J 1105, and this will be of course in volt amperes. And if you know, this is of course the P2, that's the real part, and this is the Q2, which is the imaginary or the reactive power. Again, I can draw a diagram, power diagram for specifically a load 2. So what we have is the following. We have the imaginary and the real part, so the real and the imaginary. What we have is the real power specifically for the second load, and we have the imaginary power, which is the JQ2, and of course we have the apparent power, which will be the vectorial sum of both of those, and we have this arrow, which will be S2. And again I have theta, and this is specifically theta 2. So how can I calculate now the theta 2? If I know P2, S2 or Q2, two of the three, I can calculate. I already know the P2, now I already know also the Q2. So actually the situation is for me clear. I can use tangent, for example. I can use tangent of theta 2, that will be Q2 divided by P2. That will bring me the following. The theta 2 will be the arctangent of Q2 divided by P2. So let's write down, let's fill in the values. So we have the following. Q2 is 1105 divided by 2000, which will produce almost 29 degrees. So that's actually the theta 2. Now comes the following, the power factor itself. Because this is a theta is positive, there is a positive phase, we know that there's a lagging, so we already know that the PF2 will be cosine of 29 degrees lagging. That is very important, so don't forget lagging or leading when it's a negative phase, of course. So what is the value here? It will be 0.88, almost lagging. Okay, so that's actually for question A. The whole business for question A is done. Now let's move on to question B. The question B required a power factor correction which is shown here. Calculate the required parallel element. So I will place a parallel element here, such that the total power factor of 0.7 lagging will increase to 0.95 lagging. Okay, how do I do this? Let's move again to the diagram, power diagram, but specifically we are looking at the total apparent power. So that's actually very important. So let's move on, and I will use this, of course, and I will redraw this again, and then make a improvement such that the 0.7 will increase to 0.95 for the power factor. So let's move on to question B. Okay, question B. So what do I have? I have again the power diagram. Let's draw this. We'll make the situation also clear. So what did I have? I had the following. I had the P total. This was originally, and I had an S total. That was originally, and there was also the Q total. So JQ total. This is what we had before the parallel element was placed. So after the parallel element is placed, this phase, which is designated here as phi total, must reduce to a specific value. But what is the value of that? Let's calculate that first. So the PF total, the new one, so I make a prime, will be equal to 0.95 lagging. That is actually the required value for question B. This will result in theta total prime, again using our cosine of the PF total. We already know the formula, so this will be approximately 18 degrees. So I will reduce this phase from, which was 46 degrees, all the way to 18 degrees. So let's make the drawing. So I will make it in black. So I will move from the origin and then make a S total prime, and this phase here, let me make it in red. This phase is phi of theta total prime, and that must be equal to 18. And if I have the imaginary value or the reactive power, that must be also Q total prime. So what we have? We need to reduce the inductive reactive power, of course, from this value to this value. It can be only done using a capacitor. So this distance from Q total to Q total prime must be supplied by QC, and that is actually a capacitor. So we need to calculate the capacitor reactive power, and from that we need to calculate the capacitor value C. So in this question we haven't specifically mentioned the capacitor. We only know that it's a parallel component, so we already determined, since we need to reduce, we need a capacitor. There is no inductor necessary, because if you use an inductor, this will only increase, or you will also increase your phase. That will also reduce your power factor. So that's actually not the required situation in this question. So let's first calculate the situation for Q total prime. How can we do this? So let's first use this triangle, because we know this arrow from this point to that point is exactly from this point to that point. So that means the following. I can write the tangent of theta total prime is Q total prime divided by P total prime. This is actually the basic formula. If we now substitute the values, what we get is the following. Tangent of 18 degrees, that will be equal to Q total, which is still 5000, so that doesn't change, and Q total prime. So this will give us Q total prime, which is equal to 1644 volt amperes reactive. Now, since I know that the QC is equal to Q total minus Q total prime, I know that QC must be equal to, since Q total was 5103 minus 1644, I will have 3459 volt amperes reactive. Okay, I'm really close because I know that this is the reactive power for the capacitor. So since we know that the reactive power of the capacitor can be expressed in the following way, so the QC is equal to the VC RMS squared divided by X of C. And we know the capacitor voltage RMS value of that is equal to the supply voltage and RMS value of that, and which is already given is 220 volts. It's just we already given the supply voltage in RMS, not in amplitude, so we can take it over. So what we get is the following. So let me write this down. QC is 3459 is equal to 220 quantity squared divided by QC. So what is QC? QC will be 14 ohms, and we know again QC is equal to 1 over omega times C, and C will be equal to 1 over omega times XC. So if I calculate, the C is 1 over omega times XC. What is omega? We already given the omega. This is 50 Hertz. So omega is 2 pi times F. So I will write down here. So omega is 2 pi times F, and F is here 50. So I will have 2 pi times 50 times 14. This will result in 227 microfarads. So that is actually the result for question B, and that will conclude actually this example 4, which we have dealt with two situations, one for two loads, which is specifically required such that we can determine the information for load 2, and in question B we have again looked to the total circuit and increased the power factor from 0.7 to 0.95. So I will zoom out a little bit so you can see the whole situation. So that was it, and we continue of course with the other topics and other examples in this YouTube channel. So keep in touch and don't forget to share, and see you next time.